Hello, friends. Welcome back to our third part of working of transistors in our Electronics Made Easy series. In the first part, we have seen what a transistor is made up of, and in our second part, we have seen the physical explanation about the functioning of a NPN transistor. Yes, we had some confusions, so to simplify that, to clarify the confusions. So let us just look briefly the energy band diagram of a NPN transistor. And when you are talking about a NPN transistor, yes, this is N. So our energy Fermi level is near conduction band. This is P, and hence our Fermi level is at the near valence band, and this is again another N, so Fermi level is near the conduction band. So this is the situation when we started, but when they are fused together, then they cannot remain like this, as we discussed in our PN junction lecture. So the electrons from this N region starts moving into P region, and therefore energy in the electrons energy in n region gets reduced, energy with the p region gets increased, and this imbalance in the Fermi levels keep reducing, and finally it diminishes. So if we want to continue our discussion, instead of talking with two lines and Fermi levels and all that, so let me just try to use only the lower end of the conduction band for our purpose. So what happens when these three layers are fused together? A junction is formed here, a junction is formed here, and this junction is called base emitter junction, and this junction is called base collector junction, because I'm sorry, this is emitter, this is base, and this is collector. Emitter is of moderate size, base is of very narrow size, collector is of large size. So when this imbalance in the Fermi levels get reduced to zero, then just the upper part of the lower end of the conduction band looks this way. So this is our emitter, N region. This is our base, P region, and this is our collector, another N region. That's what is the situation, and at room temperature, some electron hole pairs are generated. Okay, and because of the pentavalent impurity added, a large number of electrons are generated here, a large number of electrons are generated here. But yes, if you just enlarge this, there is a gap between the highest energy any electron is possessing at a given time and the minimum energy required to get into the base, that is the energy gap we had, and this is the minimum energy we need to supply, and to make sure that these electrons cross the junction, this gets forward biased. We forward bias this one, and because of which the electrons start flowing into the base. In the base, a small number of holes are available, and these holes will make these electrons to occupy. And because of very narrow width of the base, the electrons which are pumped into this will fall eventually into the collector region. We don't need any extra uh, energy for these electrons to fall into this, because if you look at a energy diagram, then the energy when the electron is in the base is having higher compared to the highest possessing energy possessing electron. Therefore, this electron is having higher energy compared to these electrons, so they just get into, it's like a water falling from high elevation to a lower elevation, so the this electron just gets in. But as we discussed here, we want to take them out, and for taking them out we connect this in this form. Now when we connect this, then what would happen to this energy diagram is, this was our base, the emitter side gets elevated, the emitter side gets elevated, whereas the collector side is pulled down. So the electrons here are free to enter into the base. Few holes are there which trap these electrons, whereas rest of the electrons just fall into the collector. Yes, this is the real situation. When you look at the situation in terms of energy, things will be very clear. Here there is a barrier, and this barrier will not allow electrons to flow into the base. So you need to overcome the barrier. To overcome the barrier, a potential is applied in this way, which is what we call the base emitter junction is forward biased. So because of forward bias, this gap reduced, and hence the electrons are now having sufficient energy to cross this barrier and get into the base region. And when they are getting into base region, they are accelerated, and because of their acceleration they are pumped in, and by the time they realize that they are in the base, they have reached end of the base, and they just fall down. Very few of the electrons get a chance to sit on the holes, because very few number of holes are available here. Rest of the electrons are pushed into the base collector, and this continues. So just to make sure that the electrons are pulled out again, to maintain the equilibrium, we need to reverse bias the base collector junction. So if you look at this, the electron which is there in the base can easily go into collector, because electron here in the base, which is a p-type material, is a minority carrier. So please don't get confused with the name minority majority. The minority carrier, as we discussed in our earlier lecture, in p-type, majority carrier is hole, minority carrier is electron. In n-type, majority carrier is electron, minority carrier is hole. So whether whatever is the number in p-type, it is electron is called a minority carrier. And as we have seen in our reverse biased junction, in reverse bias condition, only minority carriers will participate in conduction. Therefore, in our case, the name minority may confuse, it's misleading, because These majority carriers which were there in emitter were pumped into base. So now they are being minority and they cannot stay in that. So they occupy hole, very few number of holes. So majority of them are pumped into collector. They just fall into collector. And to make the fall more guaranteed, the collector valley is further deepened, and hence you can be assured that any electron which gets into base, if it doesn't find any hole to occupy, then it has to fall into the collector region, and hence to continue with the equilibrium, these electrons will be pulled out and so on. Done. So the whole this equation, what you call 1001 microampere is the emitter current, 1 microampere is the base current, and 1000 microampere is the collector current, is the equation. This is because the imbalance in the doping concentration between emitter and base was 1001 is to 1. So this 1001 is to 1 is going to create all these wonders. So 1001 charge carriers were created here, only one was created here. So 1001 get into this region, one combines with the other type of charge carrier, and the remaining 1000 continue and fall into the collector. So this makes 1001 microampere, 1 microampere, and then this happens to be 1000 microampere. Okay, now let's look at some other statistics. Let's increase this voltage. Because of this increase in this voltage, what would happen is, let's assume that the speed of the electrons increased, and because of which in the given period where earlier 1001 electrons were moving on in this path, now they are doing in the same time one, not more once but twice. So if they are doing twice, then you will have 2002 electrons cross this junction in one given time, and two get occupied in the holes in each time once. So it is doing two rounds, and 2000 get here. So that means you will have 2002 microampere current here, 2 microampere current here, and 2000 microampere current here. Further increase, so this may further increase to 3 rounds. So if they do 3 rounds, then the same 1001 electrons participate 3 times in a given time. Therefore, you can say that 3003 electrons have traveled in a given time, and 3 were occupying the base region. Rest 3000 get into the collector, and that continues. So making 3003 microampere current at the emitter junction, emitter terminal, and 3 microampere, if you can see, at the base terminal, and 3000 microampere you can see at the collector terminal. So if you just keep looking at it, one thing is very clear, that this ratio 1 is to 1000 ratio is always being maintained. If this is 1, this is 1000. If this is 2, this is 2000. If this is 3, this is 3000, and so on. So in all, what you can say is, if IC and IB, if you consider the collector current, what you call is IC, and the base current is called IB, and the emitter current is IE. So the base current and collector current, if you look at it, they are going to maintain some ratio, and that ratio is 1 is to 1000. So IC by IB is always 1 is to 1000. So if you look from emitter side, this is what it looks like. Now if you look from any other side also the same argument applies, because it mainly depends on the physical property, and that physical property is size of the three regions, doping concentration of the three regions, and the doping ratio. That's most important here. Done. Now what is it saying? So if you make 1 microampere flow in the base, it creates 1000 microampere at the collector. If you make 2 microampere to flow, it makes 2000 microampere to flow at collector. If you make base current as 3 microampere, then it makes 3000 microampere at collector. So what does it say is whatever be IB, IC is going to be 1000 times larger. Then we can say IC is 1000 times IB all the time. So if IB is assumed to be your input and if IC is assumed to be your output, then you can say, looking at this whole argument, that whatever be the input, the output will be 1000 times larger. So that's a main contribution of a bipolar junction transistor. That's it amplifies the current. So whatever is the base current, depending on this ratio, there is amplification, and this ratio is called HFE by some terminology, beta by some other terminology. So whatever be the terminology used, it is the current ratio, output current, input current ratio, and that depends on this doping ratio, and that's going to decide what would happen with this ratio, 1 is to 1000 ratio, and that is going to make the whole wonders begin. Done. Now if we have some resistance on this path, and this voltage, if you talk about as Vi, then this voltage is Vi. Because of this Vi, some current will be flowing, as we have seen in our PN junction. So the more Vi, the more current will be flowing, and the more current is at the emitter, that's the more current will be at the base, and the more current is at the base, the proportionally more current will be there at the collector, and the proportional more current at the collector is going to create proportionally more voltage at this. So this VC is what is IC into RC. So IB, so if VI increases, then IB increases. If IB increases, IC increases. If IC increases, then VC also increase. So what you can see is, with voltage, if you modify input voltage, you can see change in the output voltage. If you see this as output voltage, then if you modify input voltage, this input voltage in turn modifies base current. Base current modifies the collector current. Collector current modifies the voltage across this resistor. And voltage across this resistor is the collector current times this resistance, and if there is this resistance is having higher value, then this further amplifies the voltage here. So IB is under control of VI, IC is under control of IB because of this, and VC is because of this resistance is under control of IC, and hence in turn VC is under control of IC, IC is under control of IB, and IB is under control of input. So we can claim that VC is under control of VI. So that's logic for amplifying voltage. This itself is a current amplifier. This is the logic of voltage amplifier. And if these two are doing together, then that's the basis for power amplifier. So that's basics. If you talk in terms of energy, then the things will be easier. Why a reverse bias junction is conducting. Yes, there is always a confusion that if you look these two, it looks like one diode, and if you look these two, it looks like another diode. Then there was a very common argument. Then if we use two diodes like this, can it behave like a transistor? And the answer is definitely no, because if you talk about two PN junctions, then what are you talking about is a P, a N, and another P and another N. And if you just combine them, then what are you talking about is a P here, a N here, another, what is this? Another P here and a large N here. So if we want in our version, then we can connect them like this. Then it's something to do with a N here, a N here, and very large P here. That's one problem. Second problem, when you talk about PN junction, then both P and N sides are equally doped. So equal number of electrons and holes are there on the two sides. That's the first thing. Second thing is, if you use two such things, then you are having a very large P or a very large sized base, and therefore it doesn't behave like this. This whole wonder is created because this is very lightly doped and this region is very small. Because of small region, so majority of the electrons just are pumped into collector. If you talk of this logic, then the electrons get into this, and by the time they travel from this point to this point, each electron may get a hole on the way, and all these electrons get its partner, and they just sit there. Nothing is left to cross this. Though it is reverse biased, nothing will be there reaching this end, and they will never cross this, and this all this drama doesn't take place. So what would happen is only this forward bias junction. So only one diode keeps working, the other diode has nothing to do, and hence you don't find any such wonders possible. So we can't use two diodes connected like this to form these two junctions. Reason one, diodes means both sides are equally shaped and each one is equally doped, wherein we need unequal sizes and unequal doping, and that's what is the requirement to create these wonders. So once we are through transistors, then we have many more wonders on the way. And in our coming lectures, we just look into what all wonders we can create using this bipolar junction transistor. So till then, take care. See you. Bye.